Is it true? Can every even integer greater than 2 be expressed as a sum of two primes? Well, the word every is a challenge. But first, let's analyze a concrete example. Give me a number, any even number. M equals 1004, you say? Okay. Let's do an analysis of M equals 1004. We begin our analysis of M equals 1004 by listing all the positive integers less than 1004. For every integer I in this list, there is an integer j in this list, such that I plus j equals 1004. We say that I and j are complementary. For example, 1 and 1003 are complementary, 3 and 1001 are complementary, and so on. If I and j are both primes, we say that I and j are Goldbach numbers. Next, we remove all the even integers, leaving just the odd integers. There they are. The number 1, which is neither prime nor composite, is also removed, along with its complement, 1003. And here is the same list with primes colored green. This white-green pattern looks chaotic, but now we will slowly make sense of this pattern. The last number list contains no numbers divisible by 2, but contains lots of numbers which are divisible by 3. We construct a bar chart for divisor 3. There are 167 numbers that are divisible by 3. All of them are composite except 3 itself. We say that these numbers are congruent to 0 modulo 3. Also, there are 166 numbers that are congruent to 1 in bar 1, and 167 numbers congruent to 2 in bar 2. Note the symmetry. Our next removal operation is to remove bar 0 and its complement bar 2. This leaves only bar 1, but it removes lots of composites. Having accomplished removals based on divisor 3, there are now no remaining numbers divisible by 3, and we turn our attention to divisor 5. Here's the new histogram. 2 bars with circled labels are those marked for removal. After the removal of these 2 bars, there are no remaining numbers divisible by 2, 3, or 5, and so on for each prime divisor until there are no composites remaining. It is important to understand this process. You may want to rewind, pause, and study the histograms. The sequence of histograms for M equals 1004 is summarized by this plot. Initially, at divisor 3, there are 333 composites and 166 primes. The number of composites drops in an exponential manner and ends at 0, which is the whole idea of the removal process. The prime count also drops, but at a lower rate, because at each stage, column 0 contains lots of composites, but at most one prime, while its complement column contains both composites and primes. In other words, the slope of the white curve is greater than the slope of the green curve. This ensures that the two curves cross. But if the curves cross and the green count becomes greater than the white count, then Goldbach solutions are guaranteed. In this case, the crossover occurs between divisors 5 and 7. For values of m less than 1004, the crossover may occur sooner. For values of m greater than 1004, the crossover may occur later, but the crossover must occur. M equals 1004 is an example of a case where m has no small odd prime divisors. We now present larger values of m with this same property. Notice how similar they are. The white curve starts high, drops in an exponential manner, and ends at 0. The green curve starts at an intermediate value, drops in an exponential manner, but ends at a non-zero value. The slope of the white curve is necessarily greater than the slope of the green curve, so they cross over, ensuring solutions. As m increases and new numbers are added to the mix, the initial composite count trends upward but never decreases. Likewise, the initial prime count trends upward but never decreases. The number of composites divisible by 3 is also non-decreasing, so the removal process between 3 and 5 slowly becomes more and more dramatic. And the number of remaining composites divisible by 5 is non-decreasing, so the next removal process will also become more dramatic, and so on until crossover. The takeaway from this sequence of m's is that the plot is dependably predictable and the crossover always occurs. It should be pointed out that the removal process never needs to know whether a given number is prime or composite, only what its remainder is after division by a certain divisor. We are making no assumptions about the distribution of primes or the extent of prime gaps. We are not appealing to statistics. We do not assume the Riemann hypothesis. And there is nothing fundamentally special about values of m in this range of m's. In fact, let's look at some cases for much larger values of m. For example, those starting at 8,000 rather than 1,000. Here they are. These plots are for much larger values of m, but are fundamentally the same as those we have seen so far. Again, the white curve drops exponentially to 0, while the green curve drops exponentially to a non-zero value. The white slope is always greater, so a crossover must occur. The crossover is now occurring between divisors 7 and 11. In every case, Goldbach solutions are guaranteed. So these plots are very well behaved for values of m that have no small odd prime divisors. Now let us conclude by considering the values of m that do have small odd prime divisors. Consider the case m equals 1000. Here is its histogram sequence. As usual, we are removing the two designated columns at each stage. But wait, at divisor 5, only one column has been designated for removal. This is because 5 is a divisor of m, so column 5 is its own complement. This happens at every divisor which is a factor of m. But this is serendipitous because many composites are being removed, but at most a single prime. At divisors which do not divide m, we are removing two columns until crossover, and then until all composites are removed. See, the histograms are getting greener and greener until finally all the composites have been removed. Now let's look at the corresponding plot to show the effect. Here it is. We see that the composite curve is much the same exponential that we are used to, but the prime plot plateaus whenever we are removing a single nearly white column. We call cases where this happens serendipitous cases because the result is to inflate the number of Goldbach solutions. The prime plot may lose some of its exponential character. Still, its slope is always less than the composite slope, ensuring crossover. We conclude that the serendipitous cases also always have Goldbach solutions. In fact, these are in some sense the easy cases. Here is a sequence of serendipitous cases. Some values of m have a single factor, which is one of the divisors. Some have multiple such factors. This means that the prime curve may have a single plateau, or it may have multiple plateaus. When the divisor factors are small, like 3 or 5, the final effect is large. When the divisor factors are larger, the final effect is smaller. This is the reason that a plot of the final number of Goldbach solutions gives the illusion of chaos. But our argument is not that we have an expression for the exact number of solutions for a given m, but that there must be solutions because there must be a crossover. And our argument that the crossover must occur is valid for both the serendipitous cases and the more difficult non-serendipitous cases, which form the constantly increasing lower bound of solutions. What makes our method and our argument valid is that while the occurrence of primes may seem random, the occurrence of composites is far from it and can be exploited.